Module 10, chi-square tests and the F-distribution ANOVA. In our journey through statistics, we often come across data that requires a different set of analytical tools than we've previously employed. Our last module presents methods that let us dive deeper into categorical data, variances, and comparing multiple means. Chi-square distribution, unraveling frequency distributions. Have you ever come across a set of observed frequencies and wondered if they match what's expected based on a certain claim? The chi-square distribution is the tool that allows us to answer this question. It's particularly useful when dealing with categorical data from a multinomial experiment, an experiment with a fixed number of independent trials where each trial has more than two potential outcomes. A common way to organize categorical data is in a contingency table. These tables provide a clear view of how outcomes or categories relate to one another. A key question that often arises: are the variables independent, or do they depend on each other in some way? Through the chi-square test for independence, we can address this question head-on. This is also called a goodness of fit test. For example, suppose a medical researcher wants to determine if there's an association between smoking habits and the development of a specific lung disease. To explore this, they collect data from a sample of 300 individuals. The researcher divides the participants into two categories: smokers and non-smokers. They also categorize participants as either having lung disease or not. The data collected could be summarized in a contingency table. Of the 150 smokers, 50 suffered from lung disease, while 100 did not. Of the 150 non-smokers, 50 suffered from lung disease, while 100 did not. The researcher wants to determine if smoking is independent of developing the lung disease. In other words, is the occurrence of the disease dependent on whether one smokes? The researcher would set up a null hypothesis stating that smoking and the lung disease are independent. Using the chi-square formula, they would compute the expected frequencies under this assumption and then calculate the chi-square statistic based on the observed frequencies from the table and the expected frequencies. The formula for determining the chi-square statistic, written as an x with a flourish to the second power, is this. This means that for each value, you take the difference between the observed frequency and the expected frequency, square that difference, and divide it by the expected frequency. Add them up together and you have your chi-square statistic. In our case, given that there were 70 total lung disease incidents of 300 patients, so the total expected frequency for each group of 150 patients is 35. In the first group, smokers, the difference was 15, 50 minus 35. Square that to get 225 and divide by the expected frequency of 35 to get about 6.43. The calculation is the same for the non-smokers. The difference is 15. Squaring it and dividing by 25 gets you another 6.43. Adding them gives you a total chi-square statistic of 12.86. To determine the significance, there's a chi-square chart. In this case, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. In this case, there are 2 rows and 2 columns, so there is only 1 degree of freedom. A look at the chart shows that with 1 degree of freedom, 12.86 is literally off the charts. This indicates a very strong probability that there's a relationship between smoking and lung disease. Let's look at another example. Let's say we want to test if a die is fair. We roll it 60 times and record the number of times each side, 1 through 6, comes up. 1 comes up 8 times. 2 comes up 9 times. 3 comes up 12 times. 4 comes up 10 times. 5 comes up 11 times. And 6 comes up 10 times. If the die is fair, each side should come up 1/6 of the time. So, the expected frequency for each side in 60 rolls is 10. Plugging in the formula, we can calculate the chi-square statistic as 1. F-distribution and analysis of variance, or ANOVA. The F-distribution is a probability distribution that arises frequently as the null distribution of a test statistic, especially in the context of variance comparisons. It is positively skewed and defined only for positive values. The shape of the F-distribution depends on 2 sets of degrees of freedom, usually denoted by df1 and df2. It describes the ratio of 2 chi-squared distributions. One of the main applications of the F distribution is in the analysis of variance, ANOVA. It is used to analyze the differences among group means in a sample. The F-test is used to assess whether any of the group means are statistically significantly different from each other. For example, imagine a botanist wants to determine if 3 different types of fertilizer have different effects on plant growth. To do this, she plants 3 groups of seeds, giving each group a different fertilizer. After several weeks, she measures the height of each plant. To determine whether the differences in growth are statistically significant, i.e., not due to chance, she could perform a one-way analysis of variance. This analysis would produce an F statistic, which represents the ratio of the variability among the group means, which is the between-group variance, to the variability within each group, the within-group variance. If all fertilizers have the same effect, the null hypothesis, the F statistic would be expected to be close to 1. If, however, one or more of the fertilizers is different, the between-group variance would be larger, leading to an F statistic greater than 1. Using an F distribution table, or statistical software, the botanist could determine the critical F value for her chosen significance level, such as 0.05, and degrees of freedom associated with her data. If the calculated F statistic from her ANOVA exceeds this critical value, she would reject the null hypothesis and conclude that at least one fertilizer type leads to different plant growth compared to the others. In essence, the F distribution and the associated F-test allow researchers to make inferential statements about the relative variances or means of multiple groups, providing a foundation for many analyses in experimental research. Thank you for viewing our course in statistics. Best of luck in your studies.